Hello, everybody. Welcome to the session on interactive visualization. My name is Jens Schneider. I'm with Hamad bin Khalifa University here in Doha in Qatar. And today it's my honor to announce the first invited talk of this session given by Professor Enkelejda Kasneci. She is a professor at the University of Tübingen and heads the Human-Computer Interaction Research Group. In this invited talk, she will talk about enhancing user models through visual scan path analysis. Thank you for being here. Thanks.
Thank you very much for the introduction, Jens. I'm honored to speak in this round. I'll try to share my screen now so you can see my slides. Okay, can you see my slides? Okay, perfect. So I'm going to talk today about enhancing user models through visual scan path analysis. As Jens introduced me already, I'm heading here the chair for human-computer interaction, and I've been working during the past years on ways to integrate gaze information and gaze as input modality for efficient human-computer interaction. When we look at how we as humans or people interact with each other, we interact with the world and with each other in a multimodal way through both parallel and sequential use of multiple perceptual modalities. So, and to be more precise, in our daily interaction, gaze is definitely one of the most important information cues that we use. So, for example, think of people, when people observe someone looking in a particular direction, then their attention is shifted to the same location in space. Or on the other hand, we as humans are pretty good in reading the mind of others just from the eyes. And it's a very important feature for our daily social interactions. So for these reasons, there is actually a very long line of research trying to employ gaze as a modality in human-computer interaction. With the recent technological devices or the technological advances actually in the area of head-mounted displays, virtual and augmented reality, there has been a further push and a very strong push to make use of the gaze modality for a personalized experience, but also for interaction perspective, from the interaction perspective. So for those of you in the audience who have not worked with gaze so far, I just want to give you a little background on why this works and why we can retrieve more information from our visual search behavior. So because of some physiological restrictions, I hope you can see my mouse, we're able to perceive information very sharply at a very small area in our visual field called the foveal area, which is in the extent of 1 to 2 degrees. And if you think of it at a reading distance, it would be just 2 to 3 characters, for example. Here, the visual acuity is actually at highest and decreases towards the peripheral area where we're mostly sensitive to motion. In between, we have very simplified now, right? So we have a parafoveal area where we still perceive information, though not very sharply. So if you look at this graph here, and you think here's where we are at the foveal area where the visual acuity is at highest, you will see a very quick decline towards the periphery. So at almost 5 degrees of eccentricity, so somewhere here, we only have a visual acuity of about 30%. And that's why we as humans are kind of forced to move our eyes and also to move our heads in order to perceive the scene as a whole. So what looks like physiological restrictions on the one side is a very good source of information on the other side, because just by observing the eye movement, we're kind of able to infer actions or intentions of the user. So the vision that we pursue in my research group is that of a pervasive gaze-based human-computer interaction, where we use eye tracking methodology combined with machine learning techniques towards eye-based interaction everywhere at any time. Like as you see here, gaze contingent displays or gaze aware warning systems in, for example, in the use case of driving or gaze-based interaction with our own mobile devices. If we look a little bit at the current trends in gaze-based HCI, you will see a lot of papers dealing with the so-called multi-signal exploitations, where the gaze information is used along with other eye-related features to infer more information about the user, for example, fatigue, visual fatigue, or any other kind of fatigue, or drowsiness, whatever. And then also a trend towards so-called multimodal physiological computing, or also going a little bit into the area of effective computing, where gaze information is analyzed and combined with face and body, or for example, action recognition or emotion recognition, to enable further than truly intelligent interfaces, so gaze modeling for enriched user behavior, and ideally anywhere and anytime. There's a lot of challenges to get there, so most of them are still located in areas related to computer vision, basically dealing with robust feature extraction in the videos, so how to extract eye-related features, pupil information, the eyelids, how to develop models, without having a lot of heavily annotated data, dealing with efficient calibration issues, but also with slippage, and also further issues regarding robust signal processing, real-time and resource-saving machine learning methods, especially when you think like we currently capture gaze information at speeds around 250 frames per second. So imagine those video material and gaze position analyzed in an online fashion for many applications is basically undoable for the moment. And also there's attempts to combine gaze information with semantic information on the scene. And last but not least, a very important issue is proper investigation of the trade-off between utility and privacy in all of these applications. So how does a typical processing pipeline look like? So at the low level, we have, like in the case of head-worn eye trackers, for example, or eye tracking devices that are integrated in virtual augmented reality, we have cameras that observe the eye, so we can extract the eye-related features, like pupil, for example, from the images, and we have the scene information coming from the scene camera, and ideally we have a very good mapping of the eye features to the scene, so we have a gaze information. So all of this has some prerequisites that needs to be solved, like feature extraction and gaze mapping, calibration, slippage, and other issues that I previously mentioned. On top of this, we usually perform a so-called event detection, which means extracting fixation, saccades, and other types of eye movements, ideally in a real-time fashion. A fixation describes the type of eye movements, or basically the eye being stable on an area of interest, or the information, the visual information of that area of interest is being processed, while saccades stand for very quick eye movements that enable basically the eye, or enable us to change the focus of attention. And on top of that, but very or less investigated, is a whole area of so-called pattern analysis that deals with a visual scan path, so the order of fixations and saccades during a task. So the so-called visual search, from which we can infer action or really information related to the actions or intentions of the user. And that is actually the step on the pipeline that I will be talking about today. So if we think of the whole area or research area as a word cloud here visualized, you'll see there is a lot of motivation coming from the HCI perspective. So a lot of research is motivated also by the applications, gaming, marketing, education, web, whatever, decision making. And there's a lot of technical and methodological issues as well. So just a quick overview on what's on GAZE-related research, and I'll quickly guide you through the scanpath idea and to then start with scanpath modeling. So now I'm just asking you a very simple task, namely to find the cat in this image. And after a while, you have hopefully noticed that the cat is somehow hidden in the bottom left corner of the image. And indeed, I mean, as we measure the visual search of a participant, for example, like me or any other person, in this typical, or in this example, we had a person here doing the search, and we have the temporal order of the fixation. So we can see here that it took the person 19 fixations to get to the cat. Why? Because it's obviously not the most salient object on this image, so it's pretty hard to find, but then you see that the search stops. So all of this order that you see here, like the fixations, which are depicted here as circles with varying radii here in the case, they mark fixation durations, and then there's like simplified saccade visualization in between. So you get the order of the visual search that somebody performed to find the cat, and you also get very nicely visualized here in this example, the fixation duration at each of the parts. Scanpath research has a long history, and it goes back to the work of Yarbus in 1965. In his pioneer work, Yarbus asked the participant to view a painting here. This painting here was shown to different participant groups, and they were asked to perform different tasks. For example, they were asked to estimate the ages of the persons, and as you can see here from the scanpath, the visual attention is directed to the faces of the persons, right? They are asked to estimate, for example, the financial status of the family. So the visual attention will draw towards the objects on the scene. So the unexpected visitor painting is probably one of the most famous visual stimuli shown in the area of eye movement research. Later in 1970, Norton and Starr coined the term of visual scanpath as a fixed path characteristic of a given subject viewing a given pattern. And the scanpath analysis is a whole area of research, meanwhile quite challenging, with the aim of extracting information about different things. So if you come from the website design area or user interface design, you might be probably interesting to see what's the usability of the website, how long does the participant take to find specific things on a website, or to deal with any interface, or here as depicted, you may see scanpaths of pilots, pre-flight checklist, right? So different scanpaths. Okay, for some reason it hangs. So, and actually being able to analyze the scanpath can give us valuable insights into human behavior across different tasks. So this is just a depiction of a few of the tasks we have been working on during the past years, and working in the area of driving has definitely been one of the most challenging tasks we've worked with. I mean, if you think back of your own driving license, I mean, if you have one, of strategies, visual search strategies being taught during the process of learning, that's what we observe, what we can observe and analyze in an automated fashion during driving, that people, whenever they are supposed to take a specific maneuver, they have a visual search actually anticipating those maneuvers. Also, being able to model visual search behavior in the medical domain could be helpful not only for training purposes, but also to improve working efficiency. an area per se is probably visual search in art and sculpture. So we've worked together with people from the University of Vienna, art historians, to check for different displays in museums. This work was, for example, in the Museum of Belvedere. There's a lot of methodological work being done in the analysis of scanpath per se, but also estimating shared attention, joint attention in video data. And there's also other areas of applications such as teaching and education, where you can see that being able to analyze the visual scanpath along with semantics from the scene can be beneficial to improve the way we teach. Okay, so the question is, how could we enhance user models through scanpath analysis in order to improve usability, to make visual search strategies in different tasks more efficient, for example, for intelligent tutoring systems, or even for expertise development. And indeed, expertise development has been something that I find quite challenging and has caught my attention a few years ago when reading over the biography of one of the Grand Chess Masters, Capablanca. I came across one statement that really caught my attention and made me motivate, or let's say, give the motivation to work in this area. So if you kind of read what's on the Wikipedia page, you will see that Capablanca learned to play chess at the age of 4, so pretty young, by watching his father play with friends. And for those of you who have played chess, you probably know that this is a pretty quiet game, so nobody speaks a lot about strategy. So, but you can infer a lot of the strategic intentions behind a play just by viewing people how they play. So a question that has been in my mind for very long is, can we learn from just viewing experts? So is there any conceptual knowledge besides the perceptual knowledge that we can build up just by looking as experts look? And the work or the details that I'm going to show you in the remaining of my talk are basically the PhD work of Nora Kastner, a PhD student in my group, who's been working now for a while on expertise manifestation in visual scanpaths, and has looked at data-driven expertise and visual search recognition, expertise modeling through scanpaths, and ML and DeepL for scanpath analysis. So we will see here in my talk how we have worked with static stimuli, but I think the most challenging part will be to future develop these models for dynamic stimuli such as video data or real world tasks, like, for example, a sport expertise and so on. So I'll take you through, in the remaining of my talk, I'll take you through some radiology images in the area of dentistry. So what you see here are so-called OPT images. This is a whole panoramic radiograph of the whole mouth, which can be of valuable information to not only detect diseases related to the teeth, but also so-called second-order diseases, even such as cancer, for example, right? So in the recent years, there has been some attempt to train deep learning models to find anomalies in those images, but so far they work only for a specific type of anomalies, for example, and for those type of anomalies where you have enough data to train your algorithms with. But they, of course, cannot deal with the whole semantic information of such an image, because there's no human model that they have in behind to understand dependencies. So here you see some anomalies that go beyond the teeth area that have been annotated by experts. I have no clues what the anomalies are about, but I mean, if you look at some images that you might seen when visiting a dentist, for example, analyzing the images of the whole mouth is pretty challenging, right? So we can definitely say AI is not there yet. However, there is decision support systems that are going to come, and they'll hopefully be at the stage that they can really support decision taking in the dentistry area. For in the meanwhile, we need to train people to look at images at best and to develop conceptual knowledge on those. Just to give you an idea on what this is about, I'm showing here an OPT, and for me, as the most interesting part is somewhere here at the teeth area. And so would also someone think that is an incoming student of the 6th semester here, the orange scan path depicts the visual search of a student, of a medical student in the 6th semester, while the blue one is an expert scan path. And you see here that the expert discovered the whole image area, while a student primarily would focus on the most salient part, like the teeth part. So given that the scan paths are so different, it would be nice to have some kind of scan path models, so to incorporate those knowledge in intelligent tutoring systems, so to have something like an attention-aware tutoring system, which is able to provide or to guide the attention of a learner or of a student towards interesting areas or anomalies on those images. So the big question is, how can we analyze those scan paths in a very in an automated way and in the most efficient way? And if you look at this scan path analysis methods over the last 30 years, there's a whole taxonomy, a rich taxonomy actually, on methods which are based basically on manual annotation of AOIs and manual analysis of the scan paths. Then later on, we'll find methods that have been motivated by developments in the bioinformatics. We're looking for or mapping the scan paths to some string-based encodings and comparing those to each other. Like later on here, you also have some probabilistic models, but so far no employment of deep learning for scan path comparison. And I think now we are at the stage where deep learning approaches that include image features can be helpful and can support automated scan path classification and analysis. Just to give you an idea how that works, and so how people still do scan path analysis, it's just like you have here, you see the scan paths of the two different subjects viewing the same image, and you see that the relevant areas of information are some kind annotated here. In most of the cases, this is a grid-like annotation or some semantic annotation based on manual definitions of the AOI, which is first of all error prone, but also time consuming, as you can imagine. There is some methods to extract those areas in a more meaningful way, so called semantic segmentation, for example. And if you have pre-trained model, you can also use like object detectors to search for such semantic areas. But let's say we have those areas here. What people usually do is that they map fixations to those areas, so they're come up with the string encoding, and then the question is, the problem is reduced to some kind of a string alignment based on bioinformatic methods where you can apply a global alignment or a local alignment. A global alignment will give you a score of how similar two scan paths are as a whole, which might be a meaningful measure, but we're mostly interested, or the most interesting part in the scan paths are so-called repetitive sub-patterns, right? So typical sub-patterns that stand for different activities, for example, and they can be identified in a proper way by applying local alignment. So this is the state of the art. So most of the people still use this kind of encoding, and you can imagine that this is very time consuming and not easy to do. And imagine you have very long scan path. It is very, very time consuming, and also with regard to the computational resources. When we started to work in this area, we proposed a method called subsmash, which I'll just briefly mention here. Meanwhile, 3 years old, but so works very nicely, especially in order to find sub-patterns that are typical for scan path. So we still here employ some string encoding, where actually it's the string encoding is frequency based, and then we search for sub-patterns in the string, in the encoded scan path, and denote their frequency, and then we reduce the problem of scan path comparison to the comparison of their substrings. So it is just an idea that will give you then similar sub-patterns for in different scan paths. Let's go back to the dentistry application that we have. So because we also have very nice data and scan paths on this, let's say like here, this is an incoming student of the 6th semester before going to a specific OPT training, and then there's a scan path, and obviously there is a huge difference between this kind of scan path and this expert scan path. So they're highly recognizable. But what is most interesting is also the intermediate steps. So students that have received training, advanced student and beginning resident, because this is in order to employ efficient training, we need incremental models. So speaking of incremental models, this is what motivates the incremental model idea. Here you see the introductory level, so 6th semester students, they have the anatomical language, but they don't have the perceptual knowledge to look at the images. So they just focus on the salient areas. And then after they receive the training in the 7th semester, the image coverage will increase. And so it does with the 8th semester. Here you see students in the 9th semester and 10th semester. This is where they exit the studies. If you look at those data in the way people still use to analyze those data, namely by computing aggregated scores, like for example, fixation duration or fixation counts, you will find no differences, so no significant differences between all students. So, but even when applying something like the string comparison method, subsmash, like finding sub-patterns, or a global alignment procedure as the Needleman-Wunsch, you will see that scan paths are highly distinguishable. So there is apparent learning happening there. And what we also observe that the scan paths are more homogeneous after people have had this extensive training. So the scan paths become more similar. So the question is, can we do more OPT training for higher semesters to reduce expert resources, right? Which are then needed for resident supervision. We took a step in between and started to classify those scan paths based on deep learning methods, so CNNs. So we went a step further from scan path encoding and proposed a method called deep scan, which also takes the image properties in consideration. So instead of labeled AOIs, we use for each of the fixation so-called small image patches around fixation locations. So the idea is to mimic here areas that fall into the foveal and perifoveal perceptual area, to have them to have feature vectors corresponding to this visual intake, and then to be able to even compare similarity across stimuli. So it means like here in the example, when the yaw joint is fixated in any of the images, the fixations are considered similar, right? So, and it can also work for mirrored structures, left and right, for example. So the idea is to offer here a cross-stimuli comparison regardless of subject or the image. So what did we do in detail? This is one of our recent work in this area. We, as I mentioned before, around each fixation, we extract an image patch. So each of the individual fixations corresponds to a certain stimulus region, and we encode each of the region by a vector that describes the local image, and the encodings is generated using the output of a VBG16 architecture. You could, by the way, use any other architecture here, but we took the VGG network because it's a well-known, so the results can be reproduced very nicely and very quickly with image patches of 100 to 100, right? So we take like 5 blocks of convolutions, and each of the blocks is followed by ReLUs and max pooling. And since we're only interested in the feature extraction, we actually get rid of the fully connected and the prediction output layers because we don't need them. We just need the feature vector. By processing that in the temporal order of the fixation, we can even maintain the temporal scanpath order, so which is very nice. And this way, by having the feature vectors then aggregated, we can create a scanpath matrix, and we can use the scanpath matrix or the matrices of different scanpaths. We can compare the matrices of different scanpaths instead of doing scanpath encoding and comparing those. So the local alignment is basically done by comparing feature vectors. Here, what we did here in this work, we perform a local alignment using a variant of the Smith-Waterman algorithm, but you can do any comparison that you want. I mean, that it's not, yeah, let's say like here restricted to one comparison, a possibility. I mean, you can employ whatever you want here. So the idea is actually with going through all of the procedure and clustering the participants. So by the way, we had here in the study 57 students that 6th semester student that went through the pre-med studies, so they had the conceptual knowledge and they went through the OPT training, and we had 30 experts with a mean let's say like a mean practice of 10 years. As far as I hope I recall this correctly, but you can look up the details also in the paper. And we clustered the similarity scores of all participants using, in this specific case, agglomerative hierarchical clustering, but you can use any kind of clustering that you want here. And you can see that the scanpaths, the groups can be actually, the scanpaths between those groups are very well distinguishable. What is specific here is that experts have highly similar patterns to each other, so they look at image features similarly across all stimuli, while students have less similar patterns to each other and variable patterns over images. So they're in the process of building up their conceptual and perceptual knowledge. What we'd like to do, so in this type of the work that we're currently on, is working towards developing a gaze-based adaptive feedback. So we would like to highlight certain features of the optimal gaze patterns. For example, those areas that the student has neglected searching. So the question is, how can you build a perceptual expertise? So if we for example, would like to train people look for anomalies, let's say like we'd ask people, or we'd like to train people, look for the black holes here, then we would need mass practice, right? But showing an expert gaze, like if we show them the expert gaze with explanation, this will help to build up both perceptual and conceptual knowledge, right? So this will increase the efficiency of training. That is what we aim for in the way of dynamic expert modeling. And the step of the work that we're currently experimenting with is so-called subtle gaze guidance. What we do there is in general, we don't want to include any information on the image, so we would let an AOI pop up when this AOI would be in the peripheral field of the user, right? So it would be just like with the aim of guiding the user's gaze towards that part. And then it would basically, when the attention is drawn towards the AOI, this kind of circle is removed. I can also give you some preliminary results of this work that we started with the students. So we basically employ this kind of expert modeling and subtle gaze guidance to improve perceptual expertise. And we tried it with a small group of students. And we can see that the intervention works. So it's highly usable and has great potential for students and trainees. And in the next step, we are basically working to get this method to have a run with a large group of students from the medical domain and have like real world data training with students. So as you can imagine, this kind of work is not only applicable to the area of dentistry, but same or similar methods can be applied to any kind of expertise development for radiology image viewing, for example, mammography or any kind of radiological images. Of course, we will continue our work in the dentistry area because we have a very good connection here to the university clinics and can employ this in the teaching process. But as you can imagine, this is not only applicable to that specific domain, right? Currently, we're exploiting different things here. So as I previously mentioned, we would like to try this gaze guidance idea in a large-scale study with students and also incorporate different ideas there to include also workload estimation during training to make intelligent tutoring systems more adaptive. Would also like to have those training possibilities for residents that can help to have a better perceptual and conceptual knowledge, or build up perceptual conceptual knowledge on the long term. And at the same time, we're still working on methodology for, let's say, efficient scanpath analysis, and having scanpath analysis, especially for dynamic stimuli, would really be a very good way to go. So all of this work wouldn't have been possible without the students in my lab. So it's time to say thank you to all of the students, and I thank the audience for their attention. I'm happy to take your questions. I hope you have a lot of questions regarding expertise development of or any other scanpath comparison ideas. Thank you very much.
Thank you very much for this very exciting talk. We have a few questions from the audience. The first one is, how well can you calibrate the gaze direction in the wild over time? So do you have to manually and explicitly calibrate each tracker, or do they normally not drift?
Okay, For this specific use case, the problem is quite simple because they sit in front of a computer, right? So they have an eye tracker integrated to the computer. So the task here is not really very challenging because they basically maintain a stable sitting position. If we're, let's say, like we would try to, or we would want to have those methods working, for example, in highly dynamic areas like sports, right? If we would like to measure expertise development in sports, then it's pretty challenging. There's a few methods. So the question there would not be rather calibration, but slippage, device slippage. And then we have a method called grip that we proposed last year and this year. I think we can deal very well with that. I give you just a short video on horseback riding, which is really quite challenging. And I think you have kind of an idea that it works well. But in general, yeah, that's really a topic, not for the desktop-based applications, but whenever you're out in the wild, then it is an issue.
Mm-hmm. So there's one question from the audience that I also find particularly interesting is, if you can predict where the user is gonna look on a screen, can this be exploited by companies doing web advertisement? And how scary of a thought is that really?
Yeah, exactly. So that is the utility that I mentioned, the trade-off that I mentioned between utility and privacy. So I think this is an issue that we all are going to address, and there is a whole community built up around the privacy areas. So my personal opinion is that the user is the data owner. So we have to be very careful on how we handle the data, especially since eye tracking data is also highly biometric. That's why what we apply on top is differential privacy. So the data is basically provided for a specific use case, and there is no way of having the possibility to retrieve any personal information out of this data. So at the moment, we're not in the process of having data shared with any other people. So the data, the user is the data owner in the applications that we work with, right? So if we think in a later stage of having, let's say, like augmented reality glasses or having virtual reality glasses, and there's a software running somewhere, there's integrated eye tracking, and those data is collected somehow, then we have to make sure that the data is stored locally, and that that's very clear for which scope is the data being analyzed and what's happening with those data, right? So I mean, there's a privacy issue that I see, and I totally agree with the idea that we have to make sure that the data is not handed over and left out of control, right?
Yeah. So one question is also for guiding the user's attention. Have you considered changes in the local contrast to guide the viewer so that you don't overlay the content?
Yeah. So this is a very good question, and I would definitely like to explore this a lot and in detail, because this is not very easy to do, right? For some of the applications, for some use cases, this might be a very good option. However, we have to be very careful in radiology images because any kind of local manipulation on the image might have a semantic meaning, right? So any structure that might appear darker or in any other resolution or however manipulated might either, let's say, like reduce semantic information that is there on the radiology image, or manipulate towards like false positives, right? So we have to be very careful there. But for many other use cases, this is definitely an option. So for the radiology image, we'll still in the process of exploring what is a good way to guide the gaze there without reducing or adding some false semantic information to the image. So it's old grayscale image. It's very hard to interpret anyway. So you need a lot of background information to be able, so you need a whole medical study basically to be able to interpret those images. Very small manipulation can damage the image. So it's not very, it's very challenging to look at those. So I'm happy if anyone wants to contribute to that. I'm happy to have more extensive discussions on this.
So there's one question, the last question, that it may happen that you have multiple optimal scan paths.
Mm-hmm.
And then the question that arises from that is how do you compute the similarity if somebody goes in a completely different pattern, or do you just look at the images? Yeah,
exactly. So, I mean, you always run in the case of having outliers, right? So that is why we would definitely like to have all of this. I mean, having like, what I've shown you is basically very clear distinctions, but also in both groups, you have huge variations, right? So you have huge variations regarding the scan paths, more in the student area than in the experts, but we've also seen like some experts variating a lot to their colleagues, and there's different features, right? So also the time they need to explore something might be an indicator, not only how the scan path looks like, but the time window which is required to explore an image might be a very good indicator of expertise. So there's a lot of issues. It's not only like pure scan path statistics. That's why it's important. I hope I have shown it in my talk that it's good to, or it's can be very useful to have all the intermediate stages to learn these variations and to be able to model them, right? So that's the point basically.
Okay, thank you very much again. And for everybody, if you still have questions, you can use the Discord chat to ask them as well. Thank you.
Yes, and also whatever you might require, you can also shoot me an email if you want to have any discussion or share data or whatever, have access to the data or whatever. I'm happy to answer those requests. Okay, thank you very much.
Thank you.
Yeah. Okay.
So our next talk will be given by Dominik Penk. He's a PhD student at the Friedrich Alexander University in Erlangen-Nuremberg, and his talk is entitled Visualization Aided Interface Reconstruction. Please.
Thank you. Thank you for the introduction. As I already said, I'm going to talk about visualization aided interface reconstruction. And since that's a fancy term, I just first wanted to give a little bit of background. So we're working together with some material scientists, and they want to investigate atom probe tomography measurements, which are basically just looking at a small sample size of a material and mapping all the atom positions and their other data like mass and so on, and storing it in a large unorganized point cloud. And in these measurements, there are things called grain boundaries. They look like this. So if you only look at the aluminum atoms of the left measurement, you see such 2D surface-like structures emerging, and they normally separate crystals of other atom types. And they are very interesting because from these boundaries and their shape, you can infer material properties somehow. And interesting properties of these boundaries are, for example, the curvature or the distance of the atoms, of other atoms to these boundaries. And for all this computation, it's very helpful to have a real surface representation, not only a point cloud. And on the right-hand side, you see one of those, a triangulation in this example. And in our work, we strove to generate basically a pipeline to get from the full point cloud to the surface representation, and we extracted some parametric surfaces, in particular B-cubic B-splines, but you can still get a triangulation by, for example, sampling them. So a little bit more in a theory terms. So we're looking for, in theory, 1 atom thick layers which separate other atoms. And another interesting property you can see in the schematic here in the center is that the emerging boundaries may intersect in non-manifold fashion. For example, if you imagine you extract the Y outwards of the screen to get the boundary, you have this Y junction, and in geometric processing term, this is not really manifold. So it's not a manifold triangle mesh anymore. Okay, as I said, we want to find get a complete pipeline going. And the first thing is that you have to actually find out which of the millions of atoms or thousands of atoms actually are part of the boundaries. And if you're an experienced material scientist, you may have some notion which type of atoms or which mass range are important, but you still have to filter the point cloud with different settings to investigate which is the right one. And for that, we provide a little tool where you can set up these filters and get a quick visualization of the resulting surfaces. And one example you see here in the center, where we once again visualize the surfaces for the aluminium atoms. Important to note here is that this is not, we don't have an actual surface representation yet, it's just a visualization. And we do so by visualizing the density field estimated from the filtered point cloud. To get this density field, we first splat all the atom positions by using Gaussian kernels. And this yields a density estimation, like you see on the right-hand side. This is a 2D slice, of course. And the dark parts are regions of high density, and white means there's basically no density in here. And when we want to visualize it, we just do ray marching on the camera arrays. So for example, if this would be a ray we're interested in, we want to find the first intersection of this ray with a boundary. And we think, we said that the boundaries are identified as a local maxima in the density field. So what we do is we step in discrete fixed size steps through a ray and look until we find 2 consecutive samples which are above a given threshold. We do this minimum thresholding just to drop out maxima that are generated by noise. And if you think about it, so if you have 2 consecutive samples, we have to check if somewhere in between them there is a critical point in the density. And if you think back to function analysis in a 1D case, a maxima is signified, there has to be a 0 crossing of the first derivative. In 3D, it's a little bit more complicated because we don't have only one direction. We have to define a direction. And we thought it's very plausible that the density should have a maximum in the direction of the normal of the surface. And why this is the case, here's an example of such a surface. And you see the blue normal here. Along this direction, the density changes very drastically. However, orthogonal to the normal, so along the surface, actually, the density does not really change, or it may even increase. So this is why we said we want to look at the first derivative in direction of the normal. But this, of course, yields another problem. If we know the normal, we also have a surface already. So we have to somehow estimate the normal. And the idea is basically the same. Since the density changes the most in direction of the normal, we just compute the Hessian of the density field, compute the eigenvectors and eigenvalues, and say that the normal is the direction of the eigenvector corresponding to the smallest eigenvalue. And okay, so we're still not done because we only know that there's a 0 crossing in between these 2 samples, but it could also be a minimum. And to be sure it's actually a maximum, we have to look at the second derivative, again in the normal direction. And this, if you do the math just defaults to the smallest eigenvalue of the Hessian matrix once again. So if we have all these things, so 2 consecutive samples about a threshold, a sign change of the first derivative, and a negative second order derivative, we know that somewhere in between there's some maxima, and we just recursively search the small interval until we're close enough and have found our position on the surface. Okay, so I also brought some examples of the result here. On the left-hand side, there's our first approach, because we thought, okay, we are visualizing a volume, so let's just do iso-value rendering or iso-surface extraction and then rendering. But there are some problems here. For once, we don't get these nice 2D surface structures because by design, iso-surfaces are always watertight meshes, so we generate a hull around the surfaces. And as I also already said, the density along the surface might change, and therefore you cannot find a single density value which generates the entire surface, and you get very many holes. I hope you see my mouse, but there are some holes in the result here on the left-hand side. Our method, on the other hand, generates nice thin surfaces, and there are no holes in there. Only at the fringes of the actual measurement data, there are some artifacts. But of course, we're not perfect. There is one parameter you have to tweak very well to get a nice result, and this is the kernel size or density estimation. If you choose the right one, like on the left-hand side, you get a nice result. On the other hand, if you choose a very large one, like we did on the right side, you will lose some data. For example, this Y junction here cannot be represented anymore. So if you choose the other extreme, so a very small density kernel size, you get a very patchy result, and at least I don't see very much detail there in there anymore. So that's also not good. So kernel size is relatively important. And another limitation is that I was talking about non-manifold intersections, and we actually kind of represent them with our visualization method. On the left-hand side, you see a close-up top-down view of such a Y junction, and you see the wings do not really connect, but one makes a sharp turn before meeting the other one. And this is just because we do trillion interpolation on our voxel data, and then therefore there cannot be a non-manifold intersection. But on the right-hand side, you see the same result in a 3D version, and for a visual inspection, it's still good enough. So we're still in the phase where we're just looking for the right filters, and therefore it's good enough. Okay, now we come to the second part of our pipeline. Once the user found the correct set of filters and yields, for example, this point cloud here, we want to reconstruct the surfaces from this point cloud. And we do so in a relatively standard fashion by first clustering our point cloud and then extracting a single surface for each of the clusters. And finally, we do a third step where we want to reintroduce global notion, and we call it stitching. So closed surfaces are actually stitched onto each other, and we generate neighborhood information. So like, for example, cluster 5 is direct neighbor of cluster 12, and they intersect in this intersection line. So for clustering, we use a very standard seed-based clustering approach, where we prefer atoms on a planar region which are densely populated. The second part of our reconstruction is generating the actual surfaces. And this is once again a multi-step approach and a multi-step approach. And we very closely follow floater al here. And the first thing here is we have to, if we have a cluster, we have to find UV coordinates for each of the atoms, because then we can just do a least square fit of the actual surface, which is then quite easy. And to find a parameterization, we first have to find out which of our atoms are at the boundary of our cluster and which are in the interior, because the boundary has to be mapped onto the boundary of our parameter space. And here we look at a single atom and its neighborhood. So for example, 32 nearest neighbors, project them onto the best fitting plane, do a Delaunay triangulation of these projected points and check if the point is in the boundary or in the interior. For example, if A would be the starting point, then A is on the boundary of the triangulation and therefore also on the boundary of the cluster, whereas B would be an interior point of the cluster. Once we found all our boundary points, we somehow have to map them onto, for example, the unit rectangle in a sensible fashion. And we thought, okay, it's relatively plausible that the boundary should be as short as possible in 3D space. And this just means that we have to solve a traveling Zeisman problem on the fully connected graph of boundary points. And we do so by starting at an arbitrary point, and as the next point, choose the one which is closest to it in 3D space. And then for the third one, the closest to the second one, and so on and so forth, until we mapped all the points. However, in many cases, then you sometimes miss one of the points in the beginning, and then you have to use these missed points in the end to close the loop, yielding, of course, in wrong boundaries. So we use the 2-op heuristic to transform this greedy starting approach into the correct solution at the end. Fortunately, there are, in most cases, very few boundary points, and therefore the entire process is quite fast. And okay, so And then we can once again do the rest of the floated ALF. When we have the UV coordinates for the outer points, we can compute the interior points, UV coordinates from them, and then fit the actual B-cubic B-spline. I think the more interesting part is the third step in our reconstruction pipeline, where we do the stitching. And as a quick note here, let's assume we want to stitch the orange surface to the gray one down below. At first, we have to find the actual intersection line depicted in yellow here. And there are two cases. In some regions, the orange surface may protrude the gray one, or like in the center here, there you can very easily find the intersection by solving basically equation saying orange surface has to be the same as the gray surface. But in other regions, you would have to extend the orange surface, like on the right edge. And to have a unified framework for solving all this, we do this extension of the orange surface using quadratic Taylor expansions. Okay, once we found the orange intersection line, we move the outer row of control points of the orange surface such that the fringe directly coincides with the yellow intersection line. It's maybe a little bit hard to see, but that's why I marked it with a yellow circle. There are still some problems in there. If you see the orange surface overlapping itself where it protruded the gray surface beforehand, and maybe stretched a little bit at the other regions where we had to extend it a little bit. And to get rid of all these errors, we just reparameterize the inside of the orange surface and then get the nice result on the right-hand side here. Okay, I also brought some results for our reconstruction pipeline. You already saw one for the Real-world data set, but we also wanted to have some quantitative reliable data and therefore generated some synthetic point clouds from known functions. And the first thing you can see in here is very nicely is that stitching actually works. On the left-hand side is a result where we reconstructed and did not do the stitching yet. And there you see there are some gaps between the center part and the wings because some points of the wings were attributed to the center part. But after stitching, these gaps are basically gone. We added two different types of noise to our measurement, to our simulated data. For once, we added uniform distributed noise in the volume, because even if you set up filters, there will still be some atoms left which are not part of any boundary. And on the left-hand side, you see the influence of the reconstruction result, and it looks, our method is relatively robust against these types of noise. And this is maybe not really obvious why this is the case, and that's because I didn't tell you one further step we did. Here you see on the left-hand side a reconstruction of all the clusters in our point cloud, and you see basically that the noisy parts generate very many small clusters and surfaces, and therefore we just allowed the user to drop low clusters and only keep the, for example, 3 highest clusters with a slider just after reconstruction. And the second noise we added was normally distributed noise around the normal of our surface. So on the right-hand side, you see a perfect sample, and then with some added noise here. And as expected, the result is influenced roughly quadratically by this type of noise. Yeah, and this was like expected. And to the last slide here, I also wanted to show you a failure case, because I don't want to show only things that work perfectly. In this example, it's very important to choose the right neighborhood size for boundary point estimation. Here we choose a very small one, and very many points were attributed as as boundary points, and then you get these strange kinks and so on in your cluster results. Okay, that's all I wanted to talk to you about, and I'm hoping there are some questions.
Thank you very much. Very interesting way of getting these surfaces out of the data. We have some questions from the audience. Really cool way to get the surfaces. As for the kernel, have you tried only regular ones or also anisotropic ones?
We actually only tried isotropic Gaussian kernels. Because if you wanted to use anisotropic, maybe you could if you have some notion how the structure of the data is already, but at least I didn't have any. Mm-hmm. Maybe if you have some particular materials. Actually, it's very interesting. There are sometimes also 1D structures in there, so lines of atoms. And for them, it would be maybe interesting to use anisotropic ones if you know that they're in a particular direction.
I mean, one option could be that you do a two-pass. So you first extract the isosurface, not the isosurface, the surface, and then you align the kernels with it to improve the fidelity or something like that.
That would be a good idea, for example. Yeah, but as I said, the visualization is actually just the main important part for, at least for material scientists, are the surfaces in itself, and not the visualization.
So another question is, how does the performance compare to regular isosurface extraction?
So it's for different parts. For visualization, it's roughly the same because we do it in real time, though they're, I think, depending on the data set, they're up to 35 frames per second, so this is fast. If you would actually do the isosurface extractions, for example, with marching cubes for generating the surface in itself, so the second part of our pipeline, then we are much slower, much slower. So I'm talking about for a big data set, we will need maybe 1 to 2 minutes for the actual everything. So clustering, stitching, extraction, and so on. And if you do isosurface reconstruction, you would be done in mere seconds if you do a GPU version. But as I said, the problem is you get wrong results. So it's just basically not an option, unfortunately.
Okay, thank you very much.
Thank you.
And thank you. And with this, we move to the last talk of this session. The talk will be given by Vanessa Kretzschmar. She is a PhD student at Leipzig University. And her talk is entitled Visualization Framework for Assisting Interface Optimization of Hybrid Component Design. Please.
Yeah, thanks for the introduction. I will right start. First, some motivation. So what's the work about? So in structural mechanics, the reliable component design is one of the main objectives. Especially for lightweight construction, multi-material combinations, so-called hybrid parts, are used to benefit from the different properties, and the design process for these parts often becomes very challenging. And a critical section of such hybrid parts or possible weak zones is usually the interface layer, where peak stress can be considered as a potential point of failure. So in terms of our work, our collaborators, which are from structural mechanics, are interested in a specific hybrid made of metal and carbon fiber reinforced composite, short CFRP. And there, the metal insert is further coated by a polymer, which reduces the jump in stiffness, which has been shown beneficial. The shown hybrid is also designed to provide interlocking between metal and CFRP, obviously, and while being suitable for lightweight mass construction and designed for in-plane load scenarios. And here, the engineers want to improve the design by placing cylindrical load-transmitting elements called pins onto the polymer layer, interconnecting these materials, and we sketched it here by red cylinders in the bottom right corner. And since the polymer layer is created by injection molding, displacement is considered a viable option, and it also exploits the flexibility of this manufacturing process. And they had the hypothesis that such elements can homogenize the stress distribution. But unfortunately, only a few patterns with such pins could be experimentally tested because of the high manufacturing effort and the time-consuming tests. And due to the small amount of tests, no general insights were gained. To tackle this problem, a large amount of simulations with different pin placement patterns were run in a Monte Carlo-based simulation study. And with this study, the engineers want to find insights about optimal placement strategies in terms of position and density, and this includes the number of pins that needs to be set, the location of the pins, the importance of each pin, and the resulting transmitting forces. And instead of simulating the whole complex hybrid model, they reduced this model to a simplified version shown here, where they omitted the metal part. So gray here is the polymer part, and CFRP is displayed in black. And the base specimen has 45 fixed spots, but due to a symmetry condition, this was reduced to 25 different spots containing 5 half spots. This is here the pin with the ID 1, 6, 11, 16, and 21. And since the semi-finished fiber products would not fit in a very tight space, they included a condition that prohibits direct neighborhoods in terms of pins. So furthermore, such a close setup shown here by the red rectangles would disable also low transmission by tight fit. The diagonal case shown by the green ellipses here is allowed in contrast. And using this model, they simulated over 1,000 simulations with unique pin patterns during the studies. We acquired a big data set with various fields and values. And as you guessed, we get the information about the pin configuration. And on one hand, we get the number of pins set, and on the other hand, their location. Besides the pin configuration, we got also one value for each simulation, which is the transferred force. And this value should be rather high to get a good simulation. We can also extract the Cauchy stress tensor field, which is a symmetric second-order indefinite tensor field. And this describes the amount of force per area at a given point in each direction. And from this, we could also calculate criteria describing the damage or the failure. And by default, we got the von Mises stress here. And von Mises stress itself is a yield criterion, and therefore indicates a plastic behavior instead of an elastic when this value exceeds a given threshold. Generally speaking, this criteria shows if the material has a permanent deformation and therefore a damage when exceeding this threshold. And therefore, this value should be rather small, and you can say it should be an even distribution of non-exceeding values. We get one further field called status variable 1 or damage state field, which is the result of the underlying composite simulation model, which they modeled by Helios PFA from Autodesk. This variable summarizes various states of the elements of the CFRP. And I included a table here, but to shorten things up, the lower the value, the less damaged the composite is. And in case if you're not familiar with CFRP, higher values of this indicates fiber failure. And a fiber failure is way worse than a matrix failure because the fiber has a higher stiffness in its direction. So before we were able to analyze this data set, we had to first gather some requirements necessary for the engineers. And therefore, we had some discussions and ended up with 5 requirements in total for our visual system. The first one is about the proper validation of simulations. This includes, on the one hand, deficient simulations, as simulations models are never able to cover all physical relations perfectly. And on the other hand, this should enable the detection of outliers and also the reason for their deviation. The second requirement, focus on context, is related to providing an overview, but at the same time offering methods for in-detail view and observation of interesting features. Third, comparability is almost self-explanatory, but not referred to only a one-on-one comparison of simulations, but also for subsets. The second last requirement is the analysis of the pin impact. So this requires information like the minimal amount of pins necessary for a predetermined good simulation and the optimal location, of course. And to achieve this, the visualization should assist this process by allowing for selection and comparison of pin patterns. So, and the last one is called intuitiveness, and it's a quite tricky requirement to define, but it's an essential feature. For our work, we define this as providing a visual feedback loop and a low cognitive load while processing information of the visual system. Therefore, common tools known by the engineers, like color maps, are better suited than complex tensor glyphs for stress tensors, for example. Although we agree that such glyphs could provide deeper insights into the field. Now, given the data set and given the requirement, we had to look in the literature, of course, and looked for existing approaches. We had a special focus on tensor field and sample visualization techniques, or uncertainty tensor visualization techniques. We discussed them and tried them out with our collaborators. But we found that a lot of them had the assumption of an existing Gaussian normal distribution of tensors. So this doesn't apply to our data, unfortunately. We further tested a method that was considered an intermission step for the calculation of superquadratic tensor glyphs for stress tensor by Schulz and Gillmann. And this step is shown here by the picture. And it's visually the projection of the normalized eigenvalue space projected onto a square. A similar approach was proposed by Kretzschmar et al., where they showed a shaped-spaced scatter plot to quantify the stresses into compressive, tensile, and shear stresses. Although these tools gave an overview over the whole tensor field, it doesn't cover the information over a whole tensor field ensemble properly, as we would need to render such diagrams on every position, and this would lead to clutter and occlusion. Then we had also clustering, and this method came to our mind, where we selected different points, for example, close a pin or on a pin or near a pin or far away from a pin, and cluster the tensors by different invariants like the traced. And we observed the dendrogram for it. And the here shown dendrogram is for a point near a pin. And the dendrogram let us use to identify two general groups, while the left side on this image shows a group of quite similar tensors having a low trace and a low stress magnitude. And the other group on the right consists of various different valued stress tensor. But this is only also a view for one point on the field. So to reconstruct the global view, we stored the similarity values of the last junction of these previously shown two groups in a scalar field and displayed this. But unfortunately, all these methods didn't lead to any insights, and therefore we discarded them from the framework. And since these methods failed, we decided to go a completely other direction. And therefore we built a framework tailored for this specific optimization problem. And given the multi-field nature of the dataset, we didn't see a possibility to fit all the data into one single view. Therefore, it became clear that we need multiple visualization techniques and combine them in such a way that especially the intuitiveness requirement is not being violated. We started with a parallel coordinate plot, giving a first overview. And since it can only show relations between neighboring axes, we implemented a reordering of them. And furthermore, we added the option to swap the ordering of one axis, since values like force are better when high and other like the damage state is better when low. In combination to the parallel coordinate plot, we also added scatter plots, since they can show a better insight into the relation between two values. They also offer a better zooming capability, and we implemented all the plots, so also the parallel coordinate plots, in such a way that the user could create multiple plots and multiple instances of plots. For example, if the user want to create a scatter plot matrix. To connect these things, the next logical step was to implement an interaction itself. And therefore, a modular filtering approach was added to the framework. And each filter pass of this filtering approach can be highlighted by a color in every view. And also these colors then can serve as a visual history. And it's possible to highlight one simulation as shown by the picture, or a group of simulations here for pin 8, or to refine a group. For example, refine group 8 by higher transferred forces, or even to select multiple groups. Besides the parallel coordinate plot, which we had to implement a method for the spatial representation of the pin pattern, since the parallel coordinate plot only shows us the amount of pins. And therefore, we implemented a simple coloring based on the occurrence of each pin. And this is given by a transferred function from white to green, as shown here. And the last thing we included was a scalar field display. There's not a lot to say about it, besides that we intentionally used rainbow color maps, since engineers were familiar with this kind of transfer function, although we know about its drawbacks. Next, to evaluate our approach, we set up user tasks. Although a quantitative user study would be beneficial, we decided against it, since the interface problem is a special problem of structural mechanics, and setting up a digital study providing the large data set, as well as the framework itself, has its own challenges. For the user tasks, we had 3 different tasks that we oriented on the overall goal and the requirements of the framework to cover interests of our collaborators. And we took also special care for their comments and their feedback. And since time is limited here, I will only talk about our first task. And this task was about identifying the best simulation based on transferred forces and damage state. Therefore, they first observed the parallel coordinates plots and then highlighted all simulations with a transferred force of 400 Newton or higher, selecting 227 simulations. Then another refinement was made to increase the threshold to 410 Newton, which then only selects 60 simulations. And after that, they observed the pin placement distribution of the filtered subset. And to gain insight about the relationship, they also observed the parallel coordinate plot again, and as well as the scatter plots, where the number of pins and the damage, as well as the transmitted forces, are plotted. But at this point, this didn't lead to a specific pattern, except for higher pins having a better score. Then they refined this filtering again and increased the threshold to 417 Newton, selecting only 3 simulations containing an 18-pin simulation, a 21-pin simulation, and a 23-pin simulation. They observed the scalar plots, but unfortunately, this didn't provide insights except that a crack could occur for the right outside, shown in the damage state fields. They looked into the detail about all the 3D simulations and found that the 21-pin simulation in the middle is having the highest transferred force. But the 23 simulation, the 23-pin simulation had a lower percentage of damaged area. So it's up to the user to decide which metric they want to use. And this task showed that perfectly. And in respect to our user's task, we saw that our method worked. But to really conclude that, we had to check back on our 5 requirements. And even though I couldn't cover task 2 or task 3, task 2 especially helped to verify finding outlier or detect implausible simulations. And together with task 1, it also showed that the comparability requirement was not being violated. Next, focus and context was implemented by an interactive multi-view linkage approach with different tools ranging from global to local data representation. The first and the third task instead focused more on optimal pin placement patterns and showed that we also met our 4th requirement about indicating the impact of pins and their distribution. And intuitiveness was our 5th requirement. And as I said, it's really hard to quantify. In general, our collaborators agreed on achieving this, and we can underline this by the fact that we didn't got questions like, what does this plot tell us, or how can I do this and that? And coming to the insights our tool provided, we learned that placing a big number of pins increases the amount of force the specimen can transfer. However, the engineer does not need to cover every possible pin position, since we found an optimum with lesser pin than maximal possible, which translates to saving materials and therefore to save some costs. And in terms of the positions we can leave free, the results taught us to obtain a wide coverage orthogonal to the load direction and a slightly increased density parallel to it. The only exception of this statement was found on the outside, since narrow pins in the load direction promoted a crack propagation, as previous slides showed. For the future work, we want to mention 3 key objectives and that should be tackled. First, the whole simulation study about the pin placement should be extended by using non-static pin positions, since there exist more variable cases in the reality. This requires some important changes to the visual system, and especially in terms of displaying multiple patterns at once. Another parameter to observe is the use of non-circular shaped pins, like ellipsoidal shaped, as early investigation showed the engineers that these shapes have different impact. The second objective, or the second work, would be a follow-up work to this now mentioned extended study by using the gained information about the pin placement and apply it to the original hybrid design and test this. And the last thing is maybe the most interesting one for our community, since we call for more work about uncertainty or ensemble tensor field visualization techniques. And this work then should include multimodal distribution settings, as well as explore the broad space of distributions beyond the Gaussian normal distribution. And this wish was also supported by the engineers, and they added that such a work should also try to consider physical relations as well. Now, to conclude, we presented an interesting application about a multi-field simulation ensemble for a hybrid component interface optimization problem. We tackled this by using common visualization techniques linked together and offering interaction to the engineers. And as shown previously, the engineers were able to gain insights about the pin distribution and the performance of the specimen. We also discussed the applicability of uncertainty tensor visualizations to ensemble-related problems, as current visualization methods are quite limited. So for my final remark, I want to thank you all for your attention. And if you have further questions, I'm happy to answer them.
Thank you very much. Very interesting work, and I think a wonderful use case of applying visualization to the domain sciences. Maybe I start with one question. The simulation of this, on which hardware does this run? Is this workstation grade or supercomputer grade?
This is workstation grade, so I use my own laptop.
All right. So I was asking this because when you mentioned that you can go into the ellipsoid pins, then you get more degrees of freedom because you can rotate them. And then maybe you face suddenly the need to make many more such simulations.
So yeah, in terms of simulations, of course, you would need a higher performance. But as far as I know, it's not like a huge supercomputer, but a better workstation at least. Okay.
The other question I have is the cognitive load. Did you assess that just using some questionnaire or just informal feedback of the experts?
Well, sadly, we just used informal feedback. We later then discovered the Likert scale from NASART. So for our next study, we would probably use that.
Yeah, it's still subjective. So NASA
yes,
TLX is still subjective, but it's in a sense standardized. That's why I was asking that. Okay, if there are no more questions from the audience, thank you very much for attending. Thanks to the speakers. Wonderful presentations. I really enjoyed that. And see you in the keynote. Thank you very much.